All right, our final speaker before the coffee break is Cicero Liu, who's going to be talking about zooming in on the age of exocomets with the golden trio, JWST, Gemini, and Rubin. I'm pretty jealous of that. New insights and pathways into terrestrial planet formation. All right, take it away.
All right, testing mic. Sure, thanks. This okay? The volume okay in the back? Awesome. All right, thanks, Laura, for that kind introduction. And I'll today mostly be talking about JWST and a little bit of Gemini. You can ask me about what I plan to do with Rubin in Q&A. Okay. So today, I'm mostly going to focus on a critical stage for habitability inspired by solar system, which is hypothesized to happen around 100 million years, where giant impacts and late accretion happens. So JWST really advanced our knowledge of debris disk systems. Here is a view of Spitzer 20 years ago of the famous disk Fomalhaut. And this is what we have 20 years later with JWST. So you can see that we start to resolve all structures and see expanding dust clouds indicative of giant impact kind of collisional activities in the system. So the past decade also have a lot of advances in understanding what are the cometary level of activities around main sequence stars. So I'm using exocomet pretty liberally here, but what I actually mean is falling in evaporating bodies. So these bodies could be originating from the exo-Kuiper belt analog or from the exo-asteroidal analog. And the observable signature is in the visual wavelengths where you see time variable signatures of refractory elements falling into the photosphere of the star. And so Isa Rebolito et al. Led a full sky survey of main sequence stars that consists of different types. You can see the map on the left-hand side here. But the lesson is that she found that roughly 1 in 7 main sequence stars host hot exocometary gas. And JWST really opens up to a new parameter space because previously ALMA is sensitive to cold gas that's purely emitting in the rotational states. Spitzer does not have enough sensitivity and spectral resolution to do the gas work for debris disks, at least. And JWST is really opening up us in that channel. So you might have seen on the first day of the conference, this beautiful gallery of exocometry belt in debris disks. And this is work done by Luc Matra et al. 2025. You can see these are cold dust at the outer in the outer rim of these planetary systems. And with the very cold gas reservoir and dust reservoir and the combination of hot atomic gas, this creates an overlapping sample that we can create a JWST survey on. So this is cycle 1 JWST survey that's led by Rebolito et al., in which we targeted 5 different stars that's co-hosting hot atomic gas and cold CO gas. And so today I'm only going to focus on 1 stars, and this is the star HD 131488. It's an A1V type star at 147 parsecs in Upper Centaurus Lupus. That's around 60 million years old. And it's highly inclined disk. You can see on the left-hand side, the scattered light image of this adjunct disk was the central star coated by the coronagraph. So this is a first look at the spectrum, and right off the bat, we realize there's a lot of emission signatures. And what are we looking at? So at the x-axis is the wavelengths, and the y-axis is flux. And so we put the row vibrational emission of 12 CO, and we noticed that the peak positions of 12 CO R and P branches matches with some features between 4.5 to 4.76 microns. But what about those higher emission features? What about those features that's at longer wavelengths? So we realized that this actually caused by UV fluorescence. So you can think of it as this is my curtain at my house with some fluorescent paint, and you shine some UV light on it, and it absorbs the UV photon and re-emits in the visual wavelengths. But when you touch it, it's actually not scorching hot. It's kind of coolish. So that's exactly what's happening here. So on the bottom panel here, I'm showing different vibrational level of energy that together, the sum of these reproduces the observed spectra. So the second observation that we have in our JWST spectra is the detection of both 12 CO and 13 CO isotopologues. So just zooming into an atypical region of the spectrum, on the left-hand side, you see contributions from 13 CO along with 12 CO, which allow us to fit for a 12 to 13 CO abundances in this case. Okay, so we have our model. We built a geometric sort of onion ring kind of model, including all these levels of excitation, vibrationally excited molecule populations. And I wanted to show some high-level insights that we're learning. So we're detecting the gas seem to have a geometry between 0.1 AU to 10 AU. So that's a new region that's pretty close in and can measure it with terrestrial planet distances for a later type star. And looking at the effective temperature on the left-hand side, we found that interior to 0.6 AU, the effective temperature is 450, and within 1 AU, around 330. So this gas is somewhat rotationally warm, and this is very new for us. So on the right-hand side is just vibrational temperature that reflects the average radiation field around an A1V type star. So we can also fit for column, we also simultaneously fit it for column densities and stuff like that. And this allows us to do more inferences. So on the left-hand side here is a cartoon. So when we have a column density of 12 CO, we can sort of make a naive assumption. So say that the lowest level of vibrationally excited CO and the most energetic transition line that we say it's in local thermal equilibrium. And with that assumption, you can, on the left-hand side, you can think of the red molecules here, which are the minority here, being the CO detected. And there's an unseen molecule that's collisionally excited by, that's collisionally exciting the CO molecule that we see here. And thank you. And with that assumption, we can back out some mass upper limit in two regimes. So if we assume that the CO is a leftover product from the primordial protoplanetary disk gas, then we derive a H2 mass upper limit. In the contrary regime, where in solar system coma, you see expanding gas and you see collisions of water molecules and CO molecules. So with the assumption of they are spatially co-located, we can back out a water column density. You can see that the two estimates are orders of magnitude different, which allows us to propose for future observations and to test this idea. Okay, zooming out a little bit from this one individual system, what are we learning about the system, about future prospects? So you can see that this is a plot that I made, which is using spectral type as a function of CO mass. And all the dots here were the past CO mass detections from Rebolito's survey. And you can notice that the star symbol, 1 up there, that's in orange. And that's the CO mass probed by ALMA in the cold CO emission. And what we are seeing is much lower column density, which results in a lower, almost 1 million times lower column density. So that tells us that UV fluorescence is really a sensitive probe that looks into terrestrial zone, planet zone of debris disk-like systems. Okay, so more broadly, and this is a very ambitious cartoonish scheme, which I put early on. I talked about solar system inspired model says giant collisions and delivery happens around 100 million years old. Seems that the activity that we're seeing in debris disks suggests it could be possibility of early delivery. There's some simulation work that's done on this. This is a very hand-wavy pictures, and we're just starting to be able to make some constraints on this kind of picture. So with that, I'm leading a CO fluorescence survey for debris disks. And of course, because there's two songs, I named it Cactus. And this is a sensitivity limited sample of 3 disks at the upper quadrant on the right-hand side. One of them will have a spatially resolved IFU of CO fluorescence emission, which probes the region that JWST saturates out on. And then the other 2 are long slit in the M band that uniquely look at these CO emission signatures. Okay, I think I'm over time. So I'll leave my conclusions up, which are 10 million years old systems can contain 1 million Earth's massive warm gas. And we found that JWST reveals UV fluorescence as a new probe for trace amount of gas in these young planetary systems. And I hope that using Gemini and maybe in the future Rubin, we can probe different parameter spaces to study this phenomenon. And thank you. I'll take any questions.
All right, do we have any questions? In which case, oh, all right, you go.
Hi, Cicero. That was a great talk. So you're doing this for CO, right?
Yes.
Is there any chance of doing this for other common cometary gases such as CO2?
That's a great point. So I think there's so recently there was a publication on using MIRI. So they detected CO2 in the MIRI wavelength ranges. That's pretty hot. So that's a venue to look into. That's the first detection, I think, in debris disk.
We have an online question from Brenda Matthews. Thanks for your talk. If your study is successful, could this technique be used to discover debris disks?
That's a very good question. Using gas alone, I guess I think I've never thought about that question, but I think that definitely opens up a new parameter space. The Exocomet survey that ESA looks at not only looks at debris disk, but also other main sequence stars like shell stars and other things. I'm curious to also know whether we can find gaseous materials around those stars that is beyond debris stage. Yeah.
Any final questions? There's one over here.
How can Ruben help?
Great, thank you. I was waiting for that question. So, so currently we think that from the archetypal example Beta Pictoris, we see two types of comets in that system. One is the more like Jupiter coplanar comets that's seen in light curve transit. And so you see these signatures dipping down and then the gaseous tail and dust passes in front of a host star, creating a lot of signatures. So I hope that Ruben can probe that parameter space, while the spectroscopic survey can probe both populations of isotropically distributed, like Oort-Kalk and Kuiper belt kind of object, together with the coplanar stuff. So I think they look at different parameter spaces. Yeah.
Great.
Thanks for asking that.
All right, well, let's thank our speaker again and all the speakers in this session.